Welcome to MarinEngBase. In today's video, we are going to reveal about synchro converters. In my previous video, we have discussed about AC and DC motors part 6, which is Cyclo Converter. There are three kinds of AC converters, and on the first session, we have covered the Cyclo Converter. So today we'll move forward with synchro converter. As I mentioned earlier, we have cyclo converters, synchro converters or current source inverter or the voltage source inverter, or else we say pulse width modulation inverters. So the cyclo converter, it has drawback, which means that you will not be able to produce a frequency which is above the supply frequency. But we can overcome this issue by using a synchro converter or a pulse width modulation. Actually, these later two are much simpler configuration than the cyclo converter. Okay, so in today's topic that we are going to cover about the current source inverter or synchro converter. To understand the principle, first I will use a basic diagrams and to explain you how we can produce an AC supply using a DC source like a battery. In this diagram, I am using a DC source, a simple battery. This can be a DC battery or a solar panel or some kind of any other DC source. And four switches set up with as a pair of switches 1 and 2 and 3 and 4, and then an AC load. Let's say I'm going to activate first 1 and 2 pair of switches. Right. So what happens? The positive current will pass through the switch number 1 and it enters the X pin of the load. And then the Y pin is connected to the negative terminal of the battery. So we can say the X pin is positive with respect to the Y pin of the AC load. Next, I will activate 3 and 4. Then what happens? The positive charge will enters through the switch number 3 and enters through pin Y, and the negative charges will connected through the switch 4. So this time the load is subjected to the opposite polarity than the previous state. So then we can see at first time when the 1 and 2 switches are activated, it provides the positive half. When we activate the 3 and 4, it provides the negative half. Now, by alternately activating these switches, I can produce a waveform something similar to this diagram. We call it as a quasi-sine wave. Sorry, the quasi wave. It looks similar to sine wave behavior, not that much smooth, but alternating its polarity. So we can say it's an AC supply. So this is the basic fundamental behind that producing an AC supply using a DC source. So here we need to have some mechanical activation of these switches. So what we can do, instead of these mechanical switches, we can use some semiconductor material like SCR, silicon control rectifier, or transistor like IGBT, or thyristors like gate turn off GTOs. Let's see on the next slide how we can use such electronic device to configure it to happen in automatic way. In this diagram, I have replaced that 4 switches using silicon controlled rectifiers. And I have used let's say this is a programmable controller, and this programmable controller is responsible for firing each SCR. The SCR is a three-terminal device similar to a diode, which means it's allow the current flow in only one direction. But unlike an ordinary diode, you have to supply a gate pulse, then only it will start the conduction. And this conduction will continue until the current flow through the diode becomes zero or fall below the holding current of the SCR. Doesn't matter whether that you have once applied the gate pulse, and once you remove it, it will continuously maintain its supply through the diode until unless the current flow through the SCR falls below its holding current. So this is important phenomena. Right. Now, using this microprocessor controller, let's say we have made a program that to switch these two pair of SCRs in a sequence. Firstly 1 and 2 and secondly 3 and 4. And we can program the software to alter or to vary the firing sequence frequency, and then it will alter the frequency of the supply. Let's say if we activate 1 and 2 like previous case, it activates the gate signal and the load is subjected in this polarity. Let's say if we activate 3 and 4, in that case the load will subject to opposite polarity than compared to the previous state. And by alternating this firing sequence, you can produce an AC waveform, a quasi waveform with different frequencies, which is depend on the switching or firing frequency produced by the microcontroller. I hope that you understand the principle behind a synchro converter basic fundamental. So now let's see how we can use this switching arrangement to drive an AC load, which is a three-phase supply. This is basically a production of a single phase supply. Now let's see how we can produce a three-phase variable frequency supply using the same DC source. To produce a three-phase supply, I have to use 6 ACRs, and we can see that we have connected all these 6 ACRs into the same DC source, and I can arrange or I can fire these ACRs in pairs so that the three-phase load, here it is a three-phase motor which is delta connected. So each phase will subjected to an alternating current, alternating supply according to the pair of thyristors that which we are firing. Right. For example, you see now 1 and 5 are get fired. So the phase, this phase, initially this side became positive with compared to this side. But as 2 and 4 fired, what happens? The positive current enters from this end and it leaves from this side. So the polarity has changed. So this is the basic phenomenon that we can use to give opposite polarity to an AC load. Now let's say if we can fire all these three sets of pairs, then all these three phases that you can energize as it gets an AC supply. And to vary the frequency, what you have to do is just to alter the triggering frequency or firing sequence frequency. Then this three-phase load will get a three-phase supply, which is a variable frequency. In this slide, we can see the fundamental configuration of a practical synchro converter. Instead of the battery, we are using a rectifier bridge. We call it as a control rectifier bridge because instead of normal diodes, we are using silicon control rectifier. So the output of this rectifier bridge can be controlled by the gate signals. You can increase or decrease the output current as per your requirement. So the rectifier bridge is supplied through a three-phase power supply, L1, L2, and L3. So the fundamental waveform of the supply power represented by this diagram. And once it passes through the rectifier bridge, you will get this blue color DC wave, which is not the smooth one. So we have to use a smoothing inductor. As we're using a DC link, is an inductor, so the output current will get smoothened. So we can say, because of using this DC link inductor, the input part, the rectifier bridge, become a current source to the inverter bridge. This part is the inverter bridge, same like our previous battery example. And we can use a separate driver circuit to fire up the thyristors to get a variable frequency output. And you can connect that output to a DC load. In this particular case, we connected a three-phase motor. And the output of this three-phase bridge will be something similar to this diagram. We call it as a quasi-wave pattern or six-step waveform. The fundamental behind producing such waveform, I will be speak on a different lesson. So there I'll be explaining you how exactly this frequency can produce and which sequence that you have to fire and on what time intervals of this each pairs, right? And as we have two bridges, rectifier bridge and inverter bridge, these two bridges serve two different purposes. First, the rectifier bridge, it controls the phi or the flux of the motor. As it controls the current, we can say it controls the stator flux, which means the magnetic field strength. Hence, the motor torque is controlled by the controlled rectifier bridge. If you want to increase the motor torque, you have to increase the firing rate and you have to increase the current output. And if you want to vary the speed, then you have to deal with the inverter bridge. You have to alter the firing sequence or firing frequency of the inverter bridge. Then you can vary the frequency, then the speed of the motor can be varied. So this is the principle behind of controlling a motor using a synchro converter. And other important information is to have proper commutation. The commutation means switching off a thyristor. So this commutation, there are two methods, line commutation and force commutation. Line commutation means because of the supply frequency, as it crosses the 0 point or as it gets closer the 0, the supply current or the supply current fall below the holding current of the SCR will stop its conduction. So the rectifier bridge commutation occurs as per the supply source frequency. As the supply source current gets passed through the zero axis or fall below the SCR holding current, each of thyristors will come to switch off states, and again with the next firing signal it will start conduction. But for inverter bridge, as the supply is a DC source, to happen the commutation, how it happens is using the back EMF of the load connected. Here, the back EMF of the motor. So there should be sufficient back EMF available, which makes the current through the CR fall below its holding current. To happen that, normally we have to run this motor with a 0.9 leading power factor. So let's say in low loads, let's say about 10% load, there will not be sufficient back EMF produced. Thus, there will not be able to commutation to take place of this SCR. The SCR will not get off, or it will not come to a stop. In that situation, what you have to do, you have to control the rectifier bridge, and then you can cut off the supply, the DC supply, to a zero value. Then these thyristors in inverter bridge will come to off state. And then if you want to fire it again, then you have to again switch on it, the power using the rectifier bridge. So this is how it's operate at under or the low voltage or low load situations. Let's say if your main engine or your main propulsion is using a VFD motor, then at 10% loads or below, you have to use the rectifier bridge or the control rectifier source control to have the zero output. Then your inverter bridge can get into off state. Right, it's a complex process, but you have to monitor the shaft position of the motor, and then you have to use again which thyristor to fire to maintain the correct torque or the correct rotation of the motor. Right, and next is we will move forward with the next thing. We'll use three sets of animation and to see how these frequency drives produce variable frequencies. I have rearranged the motor arrangement to show the energizing of stator poles and to show the rotation of the rotor. And here we are using a programmable, let's say this is the programmable firing circuit, and it has 3 steps of speed. The V1 is its nominal speed, and V equal to half means the half of nominal speed. V equal to 2 means the motor drives the spin at the twice of its nominal speed. Let's activate the half speed first. Yeah, in this case, we can see the firing takes place in a slow rate. The command given by the circuit to each pair of thyristors are at a slow rate, so the varying magnetic field or rotating magnetic field takes place slowly, which causes your rotor to spin slowly. Let's say if we activate the next one, let's say the V1 speed, then it starts with the speed as its normal operating speed, let's say faster than the previous states. The rotating magnetic field rotates fast, thus your rotor spins fast. In the last example, we can see we can increase the speed further. Here we can see the final speed, how it spins. It's spin much faster because the firing speed is much faster than the previous two cases, right? So I hope that you enjoy the video and now you have a clear picture about the synchro converters or frequency drivers. And if you have any doubts, please comment on the below description section, and I'll be answering to your questions. And be with me, and we'll move to final session of this VFDs, the pulse width modulation, and also